In this video, I'd like to talk to you about the E field, in particular the vector representation versus the E field line representation. I am going to assume that you are already familiar with the technique of how to map the field created by some combination of source charges by plonking down your test charge all over the place and basically figuring out how much force is exerted on this test charge by these two source charges, and then drawing the net force like so, and then this gives you the direction of the field by simply dividing by Q-test, and then the result is the field at that point. As you can see, mapping this field this way by assigning a vector to every point in physical space is a very laborious task. It is also really impossible to draw. For example, if I asked you what is the field at this point, you'd have to draw another arrow on top of the previous arrow like so, and very quickly the diagram becomes so ugly and impossible to understand that it becomes essentially useless. So physicists have another way of representing E field, and that is the lines representation. And so I'd like to contrast the lines representation with the vector representation, which is what I just drew. So the field lines representation of the E field has some very specific characteristics that I am going to be very explicit about, and you should always pay attention to. The idea of the lines representation is as follows. A charge, a positive charge, let's call it plus Q, radiates field lines outwards homogeneously in all directions, like so. And these lines stretch all through physical space all the way to infinity, and the only reason I'm stopping here is because this is the edge of my picture. The idea is that the strength of the charge is represented by the number of field lines. So I did something very specific here. I drew 4 field lines to represent this charge of plus Q. If, for example, I wanted to represent the field lines coming from a charge of plus 2Q, I would draw twice as many field lines radiating outwards, again homogeneously in all directions, like so. The next thing I'd like you to understand is that the direction of these field lines represent the direction in which a positive test charge would feel a force if you plonked it on the field line. So if you put a positive test charge right over there, it would feel a force in this direction from the field, like so. And so the direction of the field line at that point represents the direction of the force. It follows from this idea that if I had a negative source charge whose value was minus Q, again I would draw 4 field lines because it is the same magnitude as the plus Q, but now the field lines would run directly into the source charge like so, because if I were to place a test charge at some point on the field line, it would feel a force exerted by that field going directly in towards the negative source charge. The next question that arises is, what if I place my test charge somewhere in between the field lines? Does it now not feel a force because the field line is not running through it? Well, the answer is yes, it actually does still feel a force, but you have to understand what the physical interpretation of the field lines representation actually is. In the lines representation, the strength of the charge is represented by the number of field lines that the charge emits or absorbs. But the strength of the field in the field lines representation is represented by the density of field lines in physical space. So the closer you are to the source charge, you can see that the lines are closer together, so the field is stronger. As you move further out, the spacing between the lines becomes greater, and correspondingly the strength of the E field becomes weaker. If you're wondering how to determine the strength of the E field at this point in the lines representation, what you need to do is think about what other points have exactly the same strength of E field. Well, all the points that make a sphere around the source charge, like so, all the points that have the same distance r from the source charge, all these points, on all these points, the E field has the same strength, although points in different directions. So if you want to determine the strength of the E field at this point right here, what you would simply do is say that the E field is equal to the number of lines passing through the sphere divided by the area of the sphere. In this case, it would be equal to Q over 4 pi r squared, where Q represents the number of lines and 4 pi r squared represents the area of the sphere of radius r. The beauty of representing the E field as the lines per unit area is that you get this 1 over r squared dependence that we know the E field around a point source charge has. In summary, the lines representation of the E field goes as follows. The strength of the charge Q is represented by the number of lines that either radiate outwards from a positive source charge or are sucked in by a negative source charge. The strength of the E field is represented by the number of lines per unit area in physical space. The last point is that we don't actually measure Q, charge, in lines. We measure charge in coulombs, but there is a conversion factor between charge in lines and charge in coulombs, and that is a factor of 1 over epsilon 0, where epsilon 0 is equal to 8.85 times 10 to the minus 12. So, in effect, the E field produced by a point source charge is equal to Q over epsilon 0 times 1 over 4 pi r squared, which is equal to 1 over 4 pi epsilon 0 Q over r squared, where Coulomb's constant K is equal to 1 over 4 pi epsilon 0.